Let's enter to the session 7 for this year NIS 2024 on foundation models. Allow me to introduce Dr. Binod Bhattarai. I got so big of introduction of him, but when he spoke, he said he wanted to introduce a lot of things, so let me do this in this short. So he's the adjunct research scientist at NAMI. He's leading the BBMML lab, and he is also the co-founder and board of director at NAMI. He's assistant professor at University of Aberdeen, and he's the honorary lecturer at University College of London. So his lab and his primary research focus on computer vision, machine learning, multimodal, and AI innovation. So without any delay, ladies and gentlemen, let's join our hands together for Dr. Binod Bhattarai.
We have like 3 minutes. They have some power issue to fix. Till then, I can do some kind of. Maybe I can introduce my team a bit more in details and do a bit of interaction. So today I'm going to talk about self-supervised learning and active learning. So, these are some of the important components of foundational model, right? And so before starting formally the lectures, right? So I would like to introduce my lab at NAMI, which is Multimodal Learning Lab. And it is based in NAMI and University of Aberdeen. So these are my amazing team, and this team resides in NAMI and at the University of Aberdeen both. So we do research in computer vision, machine learning, medical image analysis, multimodal data, active learning, and so forth. And we do cutting-edge research in this domain. And our research are being published at the top journals and conferences like medical image analysis, CVPR, and MICAI, right? And my amazing students, they participate in these global challenges at MICAI. So we have a very good track records, like winning certain challenges like Fate Race 2021. And I forgot to mention it here, but we stood runner-up in a challenge last year at MICAI, and stood 4th this year as well. And these are our sponsors and the collaborators. The collaborators, they span across the world, and I'd like to thank them all, the sponsors and the collaborators, for helping us, joining us to do this amazing research. So this is a brief introduction about my team and a bit of advertisement, I would say, about my team. So let's dive into the agenda for today, okay? So can I start now? Right. You can see this slide, and in this slide I try to summarize the history of deep learning algorithms. If you look at here, so there are multiple architectures being proposed over the past 30, 40 years, right? For example, LUNET was, so I did go before LUNET, right? So there were also amazing works in neural networks before LUNET. But then after that, if you see, the important architecture in deep learning is DeepFest, or I can say also like AlexNet is there, right? So they were more or less in the similar years like 2012, 2013, and 2014, right? And afterwards, there are several architectures. I have already only mentioned a few of them here, you know. So were proposed in actually like multiple architecture in the same years, right? And on the bottom row, you can see the dataset size, you know, the dataset, you know. See about the data size, the number of images in each of the benchmark, and also look into the quality or the type of the images collected in the dataset. Okay. So what I'm trying to show you here is that, you know, the development of or the innovation in deep learning has been tremendous, at a very fast pace in the last few years, in a decade, right? Parallelly, the growth of the data, the size, it also has grown exponentially. So, for example, deep face was 4 million, FaceNet is 200 million, and like there are millions and millions of images in this benchmark, okay? Right. And if we look in the past few years, some of the important architecture, definitely we can name several, but if we have to pick some of them, so one of them is AlexNet. So how many of you have heard about AlexNet? I believe every one of you know AlexNet? No? Right. So it was architecture actually proposed and published at NeurIPS 2012, right? And then there is ResNet, DenseNet, and Graph Neural Network, and Vision Transformer. So you must have already used some of the architectures as well here. Okay, so these architectures are being successful to model, the complex computer vision or natural language processing tasks. And but the fact we need to also notice here is that the number of parameters of these architectures are also growing exponentially, okay? Right, so here are the benchmarks in computer vision. So if you look here, and then I put one border line of, year 2012, and try to, segregate the data set and the benchmark that were being actually proposed before this year and after this year, right? 2012. So why I kept that year as a reference is that because that year AlexNet was proposed, okay? Right? So the scale of the data, the thing that I wanted to mention here is the data set is also growing, and the parameters are also growing. The computational capacity is also growing. So that has actually helped us to train, highly, basically the model with very high accuracy that can also sometimes we term it as able to give the performance to human level performance, okay? So, but the fact is that, collecting this amount of data, how much time and the resources it requires is, we usually don't discuss, right? So how much time it takes to collect those data or the annotate, the label data and so on, right? And there are certain domains where collecting this amount of data, like millions of data, for example, in healthcare, is something impossible, okay? Right? Because of several reasons. Because this data were collected from internet, but we can't collect the healthcare data from internet because there are several privacy issues and also, so so that limits the collection of this amount of data here, okay? And you need similar in the robotics. So here I would like to show you a graph that shows a relation between the amount of data and the performance of the models, like machine learning models. These models includes shallow models linear models, not with deep architectures, and the performance of deep architectures or deep learning method in relation to amount of data. So if we see this graph, what you can see from here is with the amount of data, the linear model saturates after a certain amount of data. Even if you just add more and more data, the model can reach to a limit and the performance may not improve beyond that. But the deep learning has shown that trend that with increasing data, you must have heard about these large language models now, using billions of tokens, and even the architectures are very big, right? And they give this level of performance, and if you see the graph, this performance is increasing, okay? So the fact to notice here is that, definitely the on-level data is that something we can collect from internet, let's say for this computer vision and this kind of task. right? And this annotation of the data is still challenge for even for natural images, okay? So having said that, so this is a picture that I found on internet. So this is recently become very popular and got shared in multiple social networks. This was the talk given by Ilya Sutskever, and what he's talking about is that data is a fossil fuel that we know, everybody. I don't think I really need to give you several examples to motivate it. But what he says is that the data is now getting finite, or data is not growing in the internet. Okay, so because we rely on internet to collect the data, right? Even to train the deep learning model or even large language models, so they rely on collecting the data. But now, according to his statement, okay, the data is not growing anymore. So do you agree on it? So how? Why do you think it's not growing? That's true, but the fact is that now, according to certain survey, I didn't mention it here, 80% of the now web content are, generated by these large language models or this kind of models now. Basically, when you create your website, when you feed your content, so this, out of the images, from where you generate? From this large language model, right? So meaning, the data is being generated from these large language models, and they are fed into the internet. And eventually, we are collecting the videos, but at some point of time, we also generate, there are models to generate videos too, content creation also, it can be used, right? So the voiceover and everything. So meaning, the stagnant, it will reach into the stagnant endpoint. So now, what I mean to say here is that, spending this much amount of time, is that, okay, the performance of deep learning model totally relies on the data, and definitely let's not talk about the computational power because it's growing, right? It's getting even better and better, and the faster hardwares are there, efficient hardwares are there. But what if the data just saturates that? He's talking about he has only one internet. But what about the healthcare domain? What about the robotics domain and the other domain? There are where we can't readily get this data from the internet. So the thing is that, I'm going to discuss about these two approaches, which is self-supervised learning method, which is like a foundation for foundational model. Okay, this is the basic for foundational model that we are going to discuss, right? And if time permits, I will also discuss about active learning. So, okay, the self-supervised learning method, so the name itself says self-supervision, okay? So there is nobody, you don't need any expert or someone else, to provide you supervision, okay? Right? We'll formalize this thing in the later slides, okay? Right? And then active learning is such a paradigm that where how we can, get a small subset of data to annotate, because we might not need to annotate all the data, because there can be a lot of redundancies, right? Because we talk also, like the slide from the Ilya, it also shows that, okay, the content is redundant now on the internet, okay? So then why do you want to basically annotate them all, okay? So these are the two approaches, and then bringing them together and marrying them can actually help us to, come up with, training a self-supervised learning method followed by active learning to reduce the amount of, or the cost of annotations, and self-supervised learning method to exploit or the make use of the best use of this on-level data. Okay, so I'm showing these two bubbles. So one larger bubble shows that okay, we have tremendous amount of on-level data, and then the idea of level data is that okay, we'll use a small amount of data. Okay, right. So any questions so far? Okay, then I let you spend a bit of time here. I think I'm sure like many of you have already used different deep learning architectures and trained and utilized for different tasks. But I'll let you like spend like 30 seconds or so and then see what is the difference between this pipeline, self-supervised learning method and supervised learning method. Okay, the images are same, right? So what difference can you see here? Anyone? Can you be a bit louder, please? I mean, let's make this session interactive, right? Just I'm speaking here, and then you guys are listening. I mean, that's something I think should not be, I believe. Right.
I think the boundary of the pictures in self-supervised learning, maybe it tells something about the class.
Yeah, that's true. Yeah. So definitely dogs, right? There's maybe the image of same dog here. Okay. So the color indicates that in self-supervised learning method, the data, and this is the augmented version. Okay, the same image, right? That can actually belong to two different categories here. Okay. Right? But in supervised learning method, so if we want to train a model for downstream tasks like recognizing a dog or classifying a dog from other images, then both the images will belong to same category. Okay? Right? The self-supervised learning, there will be like examples, but this kind of labels or the supervision we can generate using these functions like geometric transformations, or we will look into some more examples, or the colorizations or masking something, and which we can easily generate from any unlabeled data. Okay, so that's self-supervised learning method, and in supervised learning, you actually need the annotations for your downstream task. Okay, right. So what is the general pipeline? Okay, we talked about foundational model, right? You have seen, we must have heard about GPT and this model, BERT and this model. But then you use ChatGPT, okay? So I'll also discuss about it, like how the ChatGPT is actually trained, okay? So basically here, there's a self-supervised learning method, so which you can train using the on-level data, okay? So you can have a bunch of data, then you can apply this kind of geometric transformations or other technique to generate the label, and then you train the model, like something like, similar to supervised learning method, okay? So you can maybe, minimize, let's say, depending upon your annotation that you generate, right? Cross-entropy loss or other kind of loss, okay? And then you use that model to initialize the parameters of your downstream task. Okay? So then, given the data that you have, which is like the annotated data for the downstream task, you fine-tune your model. And that actually will give you a better performance than something that you initialize, to train a model initializing from the random parameters. Okay? So this is something that you will have in your lab today, right? So I think you will get more clarity in the lab as well, okay? But we'll discuss a bit more in details about several techniques. What are the different techniques that can be used to train a self-supervised learning method, okay? Right, so before jumping into the details, right, I would like you to spend a bit of time to solve these two puzzles. So can you see these pictures here? Right. So the image is actually divided into the patches, right? And then there are, randomly shuffled. So I believe you can actually solve the puzzle on the left-hand side very easily. Maybe on the right-hand side, it can be difficult. Do you agree on it? Yes. Right. So why do you think we will manage to solve this puzzle easily on the left-hand side? So that's true. This is a tiger and this is a painting. So, but why do you think, I mean, it can be difficult for us to solve the puzzle on the right-hand side? That's true. So we have seen that examples multiple times. We have constructed or seen that actual image of tiger many times, right? So, okay, now let's think in a slightly different way, okay? So being able to solve the puzzle means you should be able to understand what is there in the image, isn't it? Right? So if we take multiple on-level data, I mean large amount of multiple data, and come up with some of the techniques to solve the puzzle like this, creating the puzzles, right? And make the model to solve that puzzle, then the model can understand the visual, the concept, the underlying visual concept of the images, right? Okay? So that's how, the self-supervised learning method can be crucial for us to understand the visual data, maybe not necessarily the exact, the task that we are intended to do, but definitely it will understand what kind of content is there, and it will understand the image, and that can be very useful for us to fine-tune our model. So it is something like you can say that, if you are a regular jogger or runner, then you build a stamina, right? But it does not necessarily mean you can play a football. But if you are strong and if you can run, then if we can, a coach can help you to fine-tune your skill to chase or, dribble and this thing, maybe that can help you to be a football player more quickly, rather than something, doing the training from the beginning. So this is just an analogy, okay? Right? So something similar that can be done here in the deep learning. Okay? So we can use this kind of self-supervised techniques. Okay? So now, we'll look into some of the self-supervised techniques that are being used in both computer vision as well as in natural language processing and both the domain, and how they are being useful. And these are called foundational models, okay? The basis models, right? And then how these are being useful in several downstream tasks, okay? So I'm not going into the details since it is an introductory lecture, so I'm not going into the details about the architectures or the optimizations in detail. Maybe I'll look into one case, right? But in the next lecture, another professor, he will go into more details about the architectures and how you can actually optimize and learn the parameters. Does that sound good? Right. So, language model, right? So, how many of you have heard this term for the first time? I think many of you have heard about language model, right? So then what we do in this language model is, language modeling means like understanding the structure from the textual data of the languages, okay? So if you look here, there can be a training example, something like, I saw a cat on a mat or something like that. These are the statements, okay? So in general, okay, the language modeling means you have a large corpus, right? So then you want to learn the parameters in such a way that you model, basically you tend to make the joint probability of that text, equal to 1, okay? So basically you want you to model given the context, like I saw, or you want to learn the parameters to predict the next words correctly, okay? So then you have billions of tokens, billions of sentences, then you keep on learning these parameters. So then here, so probability of something given this text, right? So there is a cat, right? So then what we want to do is that we want to increase the probability of next being word being cat given the context I saw all, okay? Right? So for that, minimizing this log likelihood, right? Likelihood means maximize the probability, but we are taking the negative, so we want to minimize this likelihood, okay? right? So I'm not really going into the details, but log, we use this log function, to make it sum over this, the product of joint distribution, right? So what we want to do is that to minimize this negative log, this likelihood. So what we have to do is that we should increase the probability of cat here and decrease the probability of rest of the remaining vocabularies. Okay. So this is in general our language model. Okay, there used to be like n-gram, bigram, and this kind of techniques beforehand, right? But we'll see like how these language models are trained these days. Okay. Right. So we talk about self-supervision. We talk about pretext tasks. I think I introduced what is pretext tasks, right? I'm sure there was in the slide, but I don't know whether I actually mentioned that or not, right? Pretext task is something like the task that we create from this, geometric transformations or this kind of functions that we apply in the images, right? Or the puzzle and so on, right? So we start with, the kind of pretext task that we apply for languages, okay? Right. So if you look into the sentences, right, and if you start masking the different words, you can see some kind of structure, that exhibits the languages, meaning syntactic and semantic structure, right? I go to school, he goes to school, right? And she goes to cinema, and something like that. Meaning like there are some verbs, and they're like the subject, verbs, and object, right? So they exhibit some syntactic structure, right? So, and then also like depending on that, the semantic structures, the semantics also differ. So this thing, I think Professor Ashutosh Modi will discuss more in detail about language modeling. But what I'm going to say here is that, we can use this, like the Marx language model, or we can use this pretext tasks, and from this on-level data, we can actually learn the parameters that that does language modeling, right? So what we do here is one of the technique is Marx language model. Okay, so in this case, so you'll have several sentences, and the idea here is that to mask a word. So you have a sentence, you basically omit that word or the mask it, hide it, right? Then you learn the representations of these words and the network parameters in order to, predict that masked word. Okay, right? That's one way of basically one of the pretext tasks that actually is used for language modeling. Okay, right. So there is another something called causal language modeling. So here in this case, unlike this masked one, which can actually mask any of the words in between as well, but this causal model this is just another technique. Okay, so like it is like autoregressive. So what it can do is it can see only the past words, but not like beyond future than the masked word. So what we'll do is here, like I am a virtual, then the network parameters are learned to predict this masked word here. Okay, there's a model like GPT, GPT-2, GPT-3, which actually are the foundational model for ChatGPT. Okay, they use this kind of techniques. Okay, right. And other than that, so what else can we use? We don't just need to rely on just masking the word, right? So maybe we can use other techniques. So other than this is next sentence prediction. So you have a text, right? Then there are several texts. So your task is that given this sentences, so your task is to predict the next word, next sentences. Meaning what I'm trying to say here is that there are different structure or the way we can design several tasks which we do not need any kind of supervision. Okay? And then still they are very useful for several downstream tasks. Right? And that are actually being widely being used. And this kind of, to train this kind of model, you don't need to really train, annotate the data, any data by human experts, right? Means you can simply make use of the on-level data, right? There can be something else, right? Sentence ordering, meaning there are some already sentences are ordered, and then we want to check if this kind of order, you can basically shuffle the order and then design the task in a way that, okay, does these two sentences actually are in order or out of order, okay? So these kind of methods are also widely being used to train the foundational model for languages, okay? So other than this, what do you think? What else you can use? What other kind of tasks you can design to learn the structure of languages, or the syntactic structure or semantic structure of the languages or the word from the large on-level data? Can you think of some new other way? Not necessarily you need to have the correct answer, right? I mean, there won't be something like correct or not correct, but it's not the only, these are not the only way, right? I mean, there can be several ways. Yep. What? Yeah, like? Yes, that also can be, right? So yeah, you was mentioning about swapping of the order of the words, right? And then, yeah, I mean, I'm just like, this is it can still be a research problem, right? But yes, so why not? So basically, this is a text only, right? So maybe you can use the images accompanied with text also, to train the longer parameters, right? Which are being used by click model or vision language models, which we'll discuss. I mean, I will introduce you later in the slides, right? Text only, right? And then, yeah. So there are several methods are there. So, but the overall goal that I want to actually introduce you here, I mean, its goal is that, okay, there is on-level data, on-level text. You can use this text to learn the useful parameters, okay, without even having explicit labels, okay? Right. So I was talking about, okay, ChatGPT in the beginning, right? So how does this ChatGPT work? Okay, so simply using this model is not the way only, I mean, basically may not help you to generate the conversation that we are intended, right? Or the conversation that we expect, right? The question that we pose, because they don't explicitly model such thing, isn't it? Okay, so then how these foundational models are being used, like for example, ChatGPT, how it works, I mean, how actually it is being able to generate the responses that we are actually looking for. Okay, so how it does is that, okay, there is like large on-level data, then we do pre-training LLM large language model using one of the techniques, or other than those techniques that I mentioned before, right? Then what you'll have is that you'll have some small level data, right? And you fine-tune that model for your task. So you can make a chatbot or the conversational engine, rely for your very niche or very specific task. If you are in a company, like, if you want to, let's say, manage your meetings or appointments, or if you want to manage your inventory, or if you want to get information about your inventory, right? This readily available GPT, I mean the GPT model may not work for you, right? So then what you can do is that you can actually collect a small amount of data and then fine-tune this model, right, for your intended task. Okay? So that's what it is. A small level data set is used, and that data set will be used to fine-tune this LLM. Okay? So if I have to just give you an example about the chat or the conversation, what will happen here is that, okay, you send some query or the prompt, right? And it generates some responses, and based on like how good are the, the good or something like that you expected, the response. Basically, it can generate multiple response, right? Then you can rank them, and you actually can send that as a feedback, okay? And meaning like there is something called reinforcement learning or other techniques, right? So based on the output, you give the reward or penalize the model, and that actually updates your parameters and help you guide to generate the responses that you are looking for your task. Okay, so that's something is done. So you have foundation model, and then you use them to fine tune for your downstream task. Okay, so even the ChatGPT is trained in a similar manner. Okay, so there is a model. I mean, we send some query, and then I think if you use ChatGPT, sometimes they will send you an option to rate the responses, right? So there will be multiple responses. So then they'll ask, hey, which response is better, right? So that's ranking, right? So based on your feedback, they actually, retrain the model. Okay? Okay, so any questions so far? So there is foundation model, so you can train, and there are another stage where you fine tune for the downstream task. Okay? No questions? So there is one question here.
Good morning, Professor. Good morning, everyone. So my question is a rather simple one, but self-supervised learning, this is the first time I'm hearing about it, but I'm drawing a lot of parallels to unsupervised learning. So can you clarify if this is a special case of unsupervised learning, or this is a completely different class of machine learning?
Sorry, I missed some part there. Can you please repeat?
No, I can draw a lot of parallels to unsupervised learning, and
You can draw, sorry, what?
parallels
Parallels.
to unsupervised learning. Is self-supervised learning an example of unsupervised learning, a special class, or is it a completely different type of class of machine learning?
Oh, okay. If I understand your question, right? So you can draw a parallel, meaning like relation between self-supervised learning and supervised learning method. Unsupervised. Okay. In unsupervised, I mean, you can use actually unsupervised means like uncovering the latent classes, let's say, right? Okay, so that's based on the features, or But what you can do is that you can use those classes to train, to generate some kind of pseudo levels, and based on that, maybe you can train in a self-supervised manner. So, but yes. So your question is that is this the same thing or different thing? Is that correct? So yeah, unsupervised means, I mean, we can say that, right? I mean, in unsupervised, it's kind of mostly you think about clustering, and let's say in simple terms, right? Then you'll have like some prior knowledge. Let's say that okay, this is the data that I have, and I believe there are some n number of classes, right? And then you basically set several number of classes, and then you try to fit the data into one of the classes. Okay, and then that carries like some underlying structure. Okay, definitely. But I mean, there is similarity for sure. Like now, basically, basically also like geometric augmentation, or we'll see, like so you can categorize them on the basis of that. In self-supervised learning, let's say the two images, like the cat and dog, actually with same rotation angle, actually can belong to same class, right? So clustering also, in what basis you want to do clustering, okay? So, but definitely I think we should be able, I think there is already some work like using clustering to generate pseudo levels and use them to train in a self-supervised manner. But yeah, I mean there is this similarity actually, yeah. Yeah, great, thanks, great question. So, yeah, so next, let's move to next part, right? So that was about languages, okay? Now, what about the vision data? I mean, this is not only the language data that we deal, right? We have images as well. So, how are we going to design those pretext tasks for images? Okay, so let's have a look. So, I mean, just let's do a quick recap here. So you have label data, that's pretty straightforward, right? That's a supervised learning method. So label data, there's a feature extractor that you learn, and then a task elements like the classifier, and you do predict and you compare them, and you compare and compute the loss and update the parameters. Okay, so there are several objective functions for that depending upon your task. And this is just before jumping into vision. I'm trying to recap what exactly it is. Okay, so self-supervised learning pipeline, right? So you have lots of on-level data, and then this is the input data. So there is feature extractor, and then split text task. So this split text task is something that we generate from different masking or let's say geometric augmentation, right? And the next stage is you use this feature extractor that you train from the on-level data, and you freeze those weights, and you train the model for your downstream task, which you collect the annotation yourself. Okay, right. So that was a quick recap. Now let's think about the visual data, right? The images or the videos. So how we can design the pretext tasks for them. I think you already got some idea because I showed you an example in the beginning itself, like to solve the puzzle, right? So that was a pretext task, like one of the pretext tasks for visual data, right? So the images these are high dimensional, so listing all the probability and choosing from one of those does not make sense, like in the text that we said, okay, this is the words, even in the words, like there can be 80,000 or 90,000, 100,000 of vocabularies, but the image can go like very high dimension, like So for example, if there is a 240 into 240, like 256 images, right? So, or the high resolution images, so it can go very, the dimension can go very high here. So how we can design this pretext task for vision is, we can apply some geometric transformation. Like, the geometric transformation can be, let's say, the rotation, or solving the puzzle, or you can do colorization of the image and decolorization of the image. Okay, so these kind of things, these are being used. Okay, so one of them is rotation. Okay, so for example, so this is an image. So you can see this thing from your side. So imagine this is an image, or this is an object, right? So if I just rotate it, so can you imagine like by how much like I rotate this mic? How much the angle, by how much I actually rotated this image? So we can easily estimate it, right? Isn't it? So this we could do because we already know what is mic is, right? So, but if I show you something like very unusual object, and then basically say that, okay, can you tell me like how much did I rotate in reference to its upright position? Then you can't say it, right? That can be difficult, isn't it? Right? So for this is the upright position, this is the mic. So okay, if I rotate it, okay, maybe I rotate it by 10 degree, further down 30 degree, and so forth, right? Meaning, something designing this kind of task to predict the rotation angle actually, helps you learn the representation that can, help you to understand the object and its size. Right? Otherwise, you can't correctly predict or estimate the angle of rotation. Okay? So that's what exactly is being used here, and the logic behind this pretext task, right? So this is there will be images, and these images will be rotated by certain angles, right? And those angles are now your labels. Okay? Right? And you can maybe, consider it as one of the cluster index. There was a question, right? So the angle that you rotated, you can consider it as one of the indices of clusters. Okay? Right. And now you make the training examples and you train your model. Okay? So this is the pipeline here. So I believe we can see them clearly. The image is there, right? So you have like rotate 0 degree, 90 degree, 100 degree, and 270 degree. So these are the classes. Now, these are the classes like the pretext tasks. You take the image, rotate it, and then you level it by how many angles you rotated it, okay? So then you will have training examples, right? And then this is the convolutional neural network. You feed this geometrically augmented or the rotated examples to these architectures. And then you learn the parameters to correctly predict their rotation angle. Okay? Right? So then you minimize this loss. You can use cross entropy loss, right? Then that helps you to inherently helps you to understand the content of the image with this kind of, minimizing this kind of loss function. Okay? Right? So this is about rotation. There is something called rearrangement. This is another pretext task for the visual data. Okay? So you take these images, you divide it into some patches like a spatial division, you rotate them like something like that I showed you in the beginning, right? So then what will happen is that you'll have like, let's say that if you have, let's say 8 patches, then, you can have how many combinations? So you basically generate you can have these combinations, and then based on that combination, so you learn the parameters to predict the correct combination. Okay? Right? So this is how you can, formulate it as a learning problem. Given the image, take them, divide them into these patches, randomly shuffle, and it will be one of the combinations, possible combination, right? And then you feed it to the network, and you learn the parameters to correctly predict that combination. Okay? So this is another pretext task. And other than this, like the colorization can also be another pretext task. And actually I'm discussing this work which are being proposed and experimented and evaluated, and they are useful. So this is yet another pretext task which has been designed and used to train the model, and they were pretty useful. So the idea here is that you can take the color images that you have, right, and they get is grayscale image. Okay, you can easily convert it to grayscale, isn't it? Now you have grayscale and color is the original image. So now you basically can fit a model or a network to predict the color image given the grayscale image, or right? In the color there will be 3 channels, right? RGB channel. So you consider grayscale as a channel, and then like this can be a network. So this is a convolutional network, right? So basically a learning network here. So you feed the grayscale image, you feed it to the network, like okay, definitely there will be convolution and then pooling and this kind of layers, right? So then the idea is to estimate the 2 other machine channel, and when you add that the estimated channel and add them with your grayscale channel, and it should help you to reconstruct or to recover the RGB image. Okay, and then you train the model to learn these parameters. Okay, right? Inpainting can also be another task that you can design. Okay, pretext task that can be used. So right. So what you do is that you take the image, you crop that image into a certain part, and then given this cropped image, you learn the parameters of your network to complete that cropped part. Okay? Right? This is the architecture I'm painting. Is anything? Is okay? Everything? Right. Shall I continue or it's okay? Huh? Okay. Right. So this given image, you need to train the parameters to to recover the missing part. Okay. Meaning like you have image, you don't need to know what is that, just you need to crop it and then train the model to estimate the cropped part. Right. So these are the several pretext tasks that can be used to train the model, and your foundational model, I would say, because this is about the foundational model, right? This lecture is. So maybe I should remind you. And then, now this is one approach, right? So if you look into these techniques that we discuss here, I mean, we just rely on single image. I mean, why should we limit ourselves to single image or the single sentences? There are so many things, isn't it? Why don't we take care? I mean, make use of multiple images, or I mean, we rely on this geometric transformation. Why we can't use multiple geometric transformation and make use of them to learn the parameters? Maybe that will help better, right? That is about the contrastive learning here. Have you heard about contrastive learning before? How many of you have heard about it? Contrastive learning. Can you raise your hand a bit up so that I can see? Oh, it's very sparse, right? Not that many. Okay, never mind, like we'll discuss about it here, right? So, right, here, also, yeah, so maybe I should also mention you here is that, the pretext task that we designed was not explicitly something, designed taking into the consideration of downstream tasks, right? There can be certain pretext tasks that can actually align more closely with your downstream task, and that may give better performance. Okay, the rotation or something like that may actually match or overlap with some of the tasks that you consider. So, but there can be some tasks, pretext tasks, maybe they may not be that related, and that can actually determine your performance for the downstream tasks. Meaning like, the overlap or the relation between the pretext task and the downstream task also determine the performance, right? So that can be meaning like, the performance of this SSL can be very specific to the pretext task, right? So here, the idea here is to contrastive learning is to now, let's not only be task specific, maybe let's look into the representations, making them smooth, or like bringing the similar image together, right? All right. So here the idea would be like, given this image, you can actually apply these different augmentation techniques, and these techniques, when you apply these augmentation techniques, these are the images from the same image, right? So then you can actually enforce your network to learn the representations in a way that, the representations of the images, the geometrically augmented images from the same image should be similar. And other than that, should be dissimilar, right? So this is the idea behind contrastive representation learning. So if you have to just formalize it here, simple formalization is that, okay, F is your network, like that you learn, or a function, right? So then X1 and X2 will be your two images. So these two images in this case would be augmented images, right? And F is your code function. So the function can be Euclidean distance, right? or you may apply cosine distance, right? There are several metrics, right? How you want to compare. Okay? So then the idea here is that, okay, if there are x1, x2, and x3, these are the randomly selected data points, then we need to train a model fx, right, in such a way that, the metric that we use, then the score between x1 and x2 belonging to same image should be higher than x1 and x3, which are different images. Okay? Right? The similarity should be higher. In that case, do you want, if you compute Euclidean distance, does it need to be higher or lower? Lower, right? Okay, this should actually come closer. Right? All right. Great. So this is anchor, there is negative and positives. So these are your initial, before learning. And there is your learning paradigm, your network. Then what you want to have here is that, the anchor and the positive should come closer. And then negative should go forward. Okay? Right, so here in the contrastive learning, representation learning, so in relation with self-supervised learning method, so given the image, what you do is that there is a reference image and X, and then basically you apply different augmentation techniques, right? So you apply, let's say, cropping in the different region, and so you generate multiple images, and the idea here is that given the reference images and then their augmentation, the representation should be similar, and for different images it should be farther. Okay? So based on this idea, there is something called Sinclair or CLR. So we will do lab on it today. Okay? That uses the same principle here. Okay? To learn the representation. What it does is that X is your original image, right? And T and T prime, these are the two augmentation techniques, two different augmentation techniques, okay? Because there can be several augmentation techniques, right? Geometrically also, like, you can take an image, you can flip them, you can rotate them, you can crop it to from the different regions, right? Okay? So these are the, or you can do colorization, or there are several ways to do that. But geometrically, cropping and flipping, these are commonly used. Right, so you generate this two augmented version, then F is your network, okay? The feature extractor, so that's the function, right? The network is also a function, isn't it? I think neural network, Professor Bronstein, he discussed about this network chat, universal function approximator and these things. I think I saw one of the slides. So yeah, so these are the functions. Right, then you generate these representations like Zi, okay, these are the feature representations, and what you want to do is that maximize the argument, it means like you want to bring them together, closer, right? Okay, then that's between the augmented version of the same image, right? But when you train a network, then you'll have batch of images, right? In a batch, it can be 20, let's say, it depends how many batch of images you take. Then what you do is that, okay, you take these images, augment them, right? Then these augmented versions, the representation should be similar, but for the other images, then this is the batch, you basically impose this constant that the representation should be farther. So other images, the augmented image of other images in the batch acts as your negative examples, okay? Right, so these are different augmentation, original, these are crop to size, flip, color distortion and Gaussian blur. So this kind of augmentation you can apply, right? And then, so here in the objective function, so what you can do here is like the similarity score, sim is similarity score, right? And there is something like tau is called temperature, so that is a hyperparameter here, right? So K will be 1 from 2 to n, because if there is an n examples in a batch, then you apply 2 augmentation for each of the images, so it will go from 1 to n. then the idea here is that you want to increase the similarity between the augmented version of an image, and so the denominator, what it says is that you basically need to minimize the similarity, right? Because we are minimizing this loss here, right? And to minimize this loss, that's a negative loss, right? To make it minimum, the numerator should go high, right? Because we are minimizing the negative log likelihood, right? So yeah. So this is the pseudocode of this Sinclair here, right? So this is pretty much what I discussed. So you have batch of images like n batch of images. So it goes from 1 to n, right? So then you have different augmentation function to basically you apply them. Then basically you compute the similarity, and then this loss function, this that we discussed here, and then you apply this loss function across all the augmented pairs. Okay? In a batch, right? Right. So this is the visually we are showing here the indices of the images. Like let's say in a batch you have 3 different images, and these are the augmented version of these images here. Okay? So then this augmented version, they will act as positive pairs, and then the images, for example, for k is equal to 0, the first 2 images act as positive pair, and the other remaining images, that will act as negative examples for that. Okay? And then you repeat it for all the pairs. Right? Okay, here you go. This is just to show you how this kind of learning algorithms actually help you to gain a very good performance even with small amount of training examples. Right? So if you look here, so there are Sinclair's, okay? There is supervised learning algorithms, and Sinclair is the proposed method, this method we discussed. And see the performance difference between randomly initialized and Sinclair initialized. Meaning you train the model with Sinclair, learn the parameters, and then you fine tune it. Okay? See the gain, the gap, right? Okay? Right. So any questions so far? Yep.
So when you augment a data, let's say a dog, and you augment and just feed the same data, so is there a risk of overfitting for that same type of same image only? And so is there a way of introducing a regularization term or something like that equivalent to it?
I mean, your question is that we apply the same augmentation, right?
Like for one image, if you apply too much augmentation for one image, then we'll kind of overfit for the...
No, but in different batch you can apply different augmentations, right? So basically it's not like a batch of image, you pass it only once, because you have to train the model it several times, isn't it? And you can apply the different numbers and number of augmentation techniques.
Yeah, but is there a set of parameters that define you only augment this image this set of number of times?
That's a good question, but I need to look into that in details. Okay, so I don't think, we maybe, but not sure to be honest. But you augment it with different augmentations and you pass it through several iterations, right? And epochs. And overfitting, and also you'll have several negative examples, It's not like the batch will remain the same. That should work as regularization. I don't think it will really be overfitting. Right? Because your negative also changes over the batch. Different epochs. But that's a good question, yeah. Thank you. Any more? Right, so then let's continue. So we have, how much time we have left, Jitin? 20 minutes? Yeah, okay. Right, I don't think I can cover active learning, but anyway. But I'll share the slides of active learning, so, which is really not related to foundational model. I mean, it's about sampling the data and how we can use them to even to enhance or complement the performance of foundational model or cutting down the need of like big data, right? Because fine tuning is like a small data, but even if we can collect very important, diverse examples, then maybe that can also improve further the performance, right? So we discuss about the text, we discuss about the images, right? So why not like we take them both if they are available, right? So this is about clip. So it utilizes both like image and text pair, right? So here is like you have a text encoder and there is image encoder, right? So this is something similar to Sinclair, right? And the Sinclair, you use the augmented version of images. So here, in these augmentations, these two augmentations, one of them will make from image and another will make from, make from the text. Okay? So that's the pretty much, otherwise the same thing here. Okay? Right. So you have text, so you can see this, a batch of images and their corresponding batch of text, and you feed them to this respective encoder, and then the idea here is that, you compute definitely the similarities between the text and their corresponding image and other images, right? And the idea here is that, increase the agreement between the corresponding text and images, right? Agreement, and decrease the agreement with, the unrelated pairs, or the, for example, for given image I, so the agreement we want to increase between I and its corresponding text, but then decrease it for other text. Okay? So you can think of like this as like image and text are two augmented images in Sinclair, right? And yeah, so then I just wanted to also give you some idea that okay, this kind of model can be used, the raw text, and can help you to perform zero sort classification. So zero sort means like no training examples, right? Zero sort. And there are few sort or one sort, right? So how this can be used is here is that, okay, so there is some kind of, it's more or less the same, like, there is text encoder, there is image, so you have an image, and you want to categorize which image it belongs to, right? So then there can be several categories, right? And there is a photo of, and then there is a placeholder, because it takes a sentences, right? That's why we create a template and wanted to feed this, replace this placeholder with different categories, and you do the matching, image and the textual representation matching, and whichever has this higher score, and we predict that as a pass. Okay? Sounds good? So this was about, like how this text and images can be used even to pre-train your model, and Clip is the one, and it is being widely being used for several downstream tasks, and it gives very competitive performance. Okay, so in regards to this, our team has done, a survey in medical vision language pre-training, especially focusing on how the medical data and their corresponding text, different modalities of data are being used for pre-training and used for downstream tasks. And this is a survey paper, and their authors are somewhere here. And if you want to chat with them, so they are here there, Prashant and Sanskar. So they have done really amazing job. And if you want to know more about, different pre-training strategies, which we can definitely, use for your computer vision task as well, go and go through the article, which is available on archive. Right, so then I have also shared some of the repository of related works that I prepared this lecture here. Use them to make the lecture. Right. We have very little time, so I want to briefly introduce, active learning. This is something not really related to foundational model, but just wanted to give you like how this foundational model can benefit with active learning. So in the beginning I mentioned you like several times, to motivate what is the role of data in deep learning and how expensive it is to label the data. I mean, if natural images, you can use, let's say, this crowdsourcing techniques to get the label, but for medical imaging or this kind of very specific domain, we need the expert. And to annotate a single data, it can cost, like hundreds of dollars and also even like hours. It's not only about money, but we don't get the time of surgeon because we have very limited experts, right? So in that case, so the idea here is that, okay, we are talking about fine-tuning. I mean, you might ask the question that, oh, okay, we have already foundational model and we don't need a very large amount of data to train a model, then why do we need to really use active learning to get the informative or the most diverse example, right? It's because even if you can increase the diversity on that, the small amount of data that you collect, it can enhance the performance, make it more robust and generalizable. Okay, so active learning is also known as human in the loop. Okay, so it's like there is on-level data, and we want to know which examples to annotate, which examples to query their labels. Do we really need to label all the data? Maybe not, right? As I also mentioned, that there can be so many redundancies. I mean, if the redundancies are repetitive or duplicate or near duplicate, right? So then just adding or feeding those examples may not help you to, generalize your model. So this is the technique where, there will be, let's say, I'll go here into this pipeline. So there is non-annotated data or, on-level data. Then there is a function to select this data to annotate. Okay? Then this function is also called sampler. This is a function. And this function will select some representative examples to the human annotator, right? Someone who labels your data. And this annotated data will be used to train your model. That's a machine learning model that's used for your downstream task, like it's a classification or regression or whatever model you use. And then you do it iteratively. Okay? You do in some different stages with some, batch or the budget side. Okay? So there are three components, which is like sampler, learner, and oracle. Oracle means human in the loop, like that queries, because it's used as an oracle because we query the label. Query means like we ask what is its label, right? So that's oracle is also called oracle. The sampler is the function that we want to use, to identify us the most useful and important example. And learner is a machine learning model, your downstream task model. Okay? So this is a comparison between this active learning world and this passive learning thing. Like in the passive learning means like you have data, you just send them all the data to query your their labels, or annotate them and just feed in and train a model. But here in the active, so there will be, the world means your data, and then active learner, it queries, it selectively identifies the examples to query their label and then train the model. So then, as I said, why active learning? Because we don't want to train them all the images because of time constraint and budget, and also like we don't want to use redundant and repetitive or non-informative or non-useful examples. Okay? And yeah, so these are pretty much clear. And here is that, this is the graph that we obtained from somewhere, like, but this is this graph depicts like amount of level data, right? 20%, 40%, and this thing, and the model accuracy. So if you compare this graph, so one is called random selection, or passive way of learning, like something that we do usually. Take the example, train, label them and train the model. And another is active learning, where you smartly select a subset of example. So if you compare the performance here, right? So there is a gap, wide gap, right? So if you just see, even with like 30%, you can get the performance of 40 or 50% of the data that is being randomly used. This is just an instance, right? Okay? So the one question is that why do you think like the performance is converged after 100% of level data? It maps to the same point. Why? Sorry?
Because all of the data is
That's true. That's the thing. Like, we basically selected all the data, right? Right. Awesome. So now this is something here is, I'll let you to study yourself. So there are different techniques to sample the data. So one is uncertainty, another is diversity, and third one is query by committee. So query by committee is something like just another version of diversity and uncertainty sampling. So the core idea I would tell you is that this uncertainty and diversity sampling, okay? So the uncertainty is like, okay, we are doing it iteratively, right? So then there is a classifier, we are training with some data, and then with reference to this classifier, so we project the data. I mean, like, for example, you can pass your remaining on-level data on this classifier, and we can estimate the uncertainty. How difficult are they to make an inference? Okay, so this uncertainty can be quantified in terms of entropy and other metrics. And based on those examples, some examples which are very uncertain, means like some examples which are like the model is very confused. Okay, maybe we could start actually selecting them and use them to label the data. Okay, right? Think about, basically, don't forget that we are doing it iteratively. Okay, so we are not using all the data, right? So we take like, let's say 20% of the data, annotate it first, then train a model and use this model to make inference on the remaining of your on-level data, which you can do it, right? And based on the prediction that model is making or doing, so you can estimate the uncertainty, okay? Let's say that if you are doing like classification, then you can easily compute entropy, right? And the entropy, higher the entropy, more uncertain, isn't it? So then you basically can select those kind of examples. So this is uncertainty sampling. So there can be entropy, so this is what you can compute, like P log P, right? And then margin also, there is something like margin slope. For example, if you are doing multi-class classification problem, so you can basically compare the difference between the prediction between the confident example and the second most confident example and their discrepancies. So this kind of metric are also being used to sample them. And then confidence, right? So these are the uncertainty sampling metrics. So meaning like, try to find the examples which the model is confused. Those examples on which the model is confused, and then use them to label and then iteratively train your model. So that's one thing. But it has some problem with this uncertainty, right? Because we just look into the examples which are difficult. Maybe it will just get biased to certain type of examples, and then may miss the information from, right? Okay, we have a couple of more minutes. It just make like easy example, and it may lack the diversity, right? It may just focus on certain class of examples, let's say. So then in that case, what you can do is that whole diversity. We want to have, different kind of examples that can, span across the whole data set, right? The representative examples of the whole data set, okay? Right? So this is something like, we also do try to do here when we select the candidates here. We want to have a whole representations of students from whole, the whole Nepal. It's not like just we wanted to, focus on certain students with some. Definitely, I'm giving you an example. Definitely, your merit matters, right? But then we also want to have this diversity, okay? Right? So meaning something similar here, okay? Try to get as diverse example as possible so that it can represent the whole data set. So for that, we can use this is course set approach. This is a course set approach is just, if I have to, explain it in a very simple term, there are the data points and you select, for example, you have some leveled example, right? So initially in the first stage, you can say okay, where are this, how we select the leveled example, right? So here we can use like this. Sometimes we can do randomly, or you can, usually we do randomly, like let's say 5 or 10% of data. And from this level data, initial in the phase, so you compute the distance between so let's say we have K centers, okay, they act as centers now, right, like centroids of a cluster, right? Then we compute the distance of this centroid with all the examples, and then make a cluster, right? We get a cluster there, and we choose the example which are farthest on that cluster. Okay, so if you see there, so these are the member of the cluster, let's say the white, the red is already level, and the white are unlevel, then we select the green one, which is the farthest from the centroid, okay? Right, so this is course set, and on the basis of it, there can be how do we compute the distances based on the feature, and yes, so these are also called territories and selection. Right? So meaning territories means there is already a leveled example, so it has its own territory, and select the example which is the farthest in the territory. Okay? Right. So we do actively. We are doing actively doing research in active learning since many years. So we have several works in this learning paradigm, and one of the work that we applied for this, colonoscopic image anomaly segmentation. So here we apply this active learning framework, and in one of the benchmark. So so the first one is randomly selected, and the later one was in between the two are the competitive other methods for active learning, and the last row was ours. And we can see with the same amount of the data that we used to train a model, the performance, there is a good performance gap. And also this is not really visible much here, because the data set was very small, 200, 400, 500, but if you have a bunch of data, then actually you can use active learning to cut down your annotation cost by 80%. Or sometimes it's 80, 70, 50%, and that's actually, not just, forget about the cost or the money, it's about your production time as well, because if you have to take training your data for a year, you can break it down to 2 months, right? Then you can speed up your product pipeline if you are working in companies, or if you want to make a company in the future, right? Okay, so this is how the different sampling techniques. So we get this image from one of our work. So these are the different clusters. The images belong to different categories, and there is, the image may not be that clear, but how, these sampling techniques are, choosing this difficult example as well as the diverse examples, right? So, so uncertainty and diversity, these are the two things. Maybe, uncertainty that relies on difficulty, and diversity covers the whole data set. And both have their own merits and demerits, because diversity, if you just focus on diversity, then maybe you will miss. Okay, 1 minute. So then maybe you will miss the difficult examples, because we want to have a good representation of difficult example, right? Because otherwise your model may not generalize. So maybe, marrying both can be an idea, and there are several works being done, how this uncertainty and diversity can be employed and, married together. to get the best out of it. And yeah, so this query by committee is just like, you know, multiple, yeah. So basically you can have multiple models to estimate your uncertainty or, you know, this diversity score, right? And you can also apply it to, like, you know, there are some work applying in active learning as well for self-supervised learning methods or in this pipeline, and they are pretty useful. Yeah, so that's what I want to stop it here. So because of time constraint, and I think I pretty much covered the main components of active learning too. Okay, so thank you so much for your attention, and I'm happy to take your questions.
Downstream and after we learn the parameter from the pretest tags, and how do we transfer the parameters to different downstream tags like classification, segmentation, and observation, even though they are different architectures?
Okay, that's a good question here, right? So basically I would say is, yeah, so if you look into this pipeline usually, right, so your question was that, do we need to have different architecture or same architectures, right? So the foundation model is mostly used to extract a feature, and that model remains frozen, okay? So what we train is the classifier, your head, classification head, okay, right? Because if we retrain it, then that's not fine-tuning, okay, right? So here it is. Go. So yeah, so this is the thing. The left-hand side in general, okay? So the left-hand side is your on-level data, then feature extractor using the self-supervised learning method. And then now basically your feature extractor is a network, like let's say, okay? Right? And that will be basically frozen, and then you have your task here. So that you can, where you can, you know, configure your task. Okay? For example, if you want to train a chatbot relying on the GPT model, then you have to rely on them, right? There is no option. Okay? Or you can do knowledge, that's different, I think. So in simple terms, I would say, yes, we rely on their pre-trained model, and then we work on this task head where you can, you know, configure on the basis of your requirement.
Good morning, sir. I am Prashansa Shrestha, and my question is that you said that active learning will decrease the time it will take to train models. And if we are filtering out data so that we only select the best data, then won't it take just as much time?
Okay, so the training, I'm talking about training time in the sense production time is, so I think it's a bit, you misunderstood it here. What I meant to say is that, okay, so you started a company, you wanted to annotate 1 million of data. So to annotate it takes a time, right? So that's what I'm saying. So, but definitely there is a computational overhead in the active learning. You have to rerun the model and this thing, right? But that you may parallelize with the different hardwares, okay? But this annotation can take significant amount of time, you know, right? So I mean to say that, you know, you start with 10% of data, train a model, and, you know, select another 10% and another 10%, and if you can match with your performance with just annotating 30% of the data out of whole data, then you can reduce your whole, like, you know, the production pipeline by 70% or this kind of time. That's what I mean to say. And yes, definitely you have to pay more price for your GPU or computational power.
Okay, sir. Thank you.
All right, great then. Thank you so much for your attention. And yeah, if you have any questions, I'm happy to take it. I'm around. So yeah, or feel free to write me an email. Thank you so much, guys.